So last time we discussed how to describe areas in 2 dimensions. And to remind you, we described areas as being pairs of vectors, where the pair of vectors, you should think about it as representing the parallelogram which it spans. And we consider two pairs of vectors equivalent if we can transform between them using the shearing or the scaling axioms, which I mentioned last time. And so in this video, I will be using this wedge notation. So this thing in the middle is called a wedge. And really, V wedge W, you should think about it as the pair VW, which I had in the last video. So V wedge W represents the parallelogram spanned by those things. And so I've rewritten the shearing and scaling axioms here in terms of this wedge notation. And remember, the reason that we modded out by shearing and scaling, or we considered these things equivalent, was because we only cared about the area and the orientation of the parallelogram, not its specific shape. And so if two things are related by shearing and scaling in the following manner, then they have the same area, and so they should be considered the same thing. And so this is a fine description when we're working in the plane, but now we want to look into higher dimensions and see if we can say something similar. So the good thing is we don't have to redo a whole analysis. This definition pretty much works out in higher dimensions as well, or at least in 3 dimensions, where we can define area elements as being pairs of vectors, modulo shearing and scaling. So let's see if this gives us everything that we want to give. So here we have a picture of R3, and we have two vectors v and w, and I've drawn in the parallelogram that's spanned by them. And what do we want out of an area element? Well, we wanted to keep track of the orientation of the parallelogram, which, as I said in the last video, should sort of be the plane which this parallelogram lies in, and it should also be able to give you the area of the parallelogram. Okay, so let's see if it preserves the orientation. Well, scaling is obviously going to leave the parallelogram in the same plane, because if you double one side of this parallelogram, for example, you aren't going to go out of the plane that it's in. And shearing also preserves the same plane that the parallelogram is in, because you're only allowed to shear one vector in the direction of the other vector. So for example, if we look inside the VW plane, then if these are V and W, then if you shear, maybe you change W to something that looks like this, but it'll still remain in the same plane. It won't like jut out of the plane like that. And so we see that the shearing and scaling axioms leave the parallelograms in the same plane if they're equivalent parallelograms. And so it gives us a well-defined notion of an orientation. And moreover, it also gives us a well-defined notion of area, in that if you're given any parallelogram, then you can actually determine the area of the parallelogram just by using the shearing and scaling axioms. So I encourage you to try and do this. Pick two random vectors, like let's say v equals 2, 3, 7, and w equals 1, 4, 6, and try and compute the area of the parallelogram spanned by these two vectors in R3. And try to do it without the cross product in the following manner. Try to find two unit vectors, let's say u1 and u2, and let's put hats to remind yourselves that they're unit vectors, which lie in the plane of v and w. So one way to do this would be to use the Gram-Schmidt process, and then try and use shearing and scaling to change this pair of vectors v wedge w into being some constant times u1 hat wedge u2 hat. And so what this is saying is that v wedge w, the parallelogram, has a times the area of this guy. And if these are orthonormal, then the parallelogram spanned by these two should have an area of 1. And so v wedge w should have an area of a. And then see what answer you get out of that. And sort of to make sure that this notion is well defined, you should check that if you picked any other pair of unit orthonormal vectors, I should say, in the plane spanned by v and w, then you can convert that into some multiple of u1 hat and u2 hat, and that multiple should also be 1. That is to say that any pair of orthonormal vectors should have an area of 1. Now there's also this question about the sign orientation, which came up in the last video. And the point is that you can never actually assign sort of to say that one area is positively oriented or negatively oriented uniformly everywhere in the plane. And that's analogous to saying that if you have some random vector in R3 or in any vector space, you can't exactly say it's going in the positive or negative direction, But what you can't say is if two vectors are pointing in the same direction or if they're pointing in opposite directions. And so similarly, what you can do here is if two area elements lie in the same plane, you can say whether they have the same orientation or the opposite orientation, depending on whether the scale factor between them is positive or negative. Okay, nice. So now we have a description of areas in 2 dimensions, which gives us an orientation and a magnitude for each of them. So we seem to have everything that we wanted. However, we're not quite done yet because remember I said that we want this set of area elements to have a vector space structure. And that's because we want to sort of replace the vector fields that we had in when we were working with Rham Cohomology. So let's see if the vector space axioms carry over to R3. And so the scalar multiplication carries over pretty easily because remember all we had to do was say, okay, if we take some scalar multiple of some parallelogram, then all we have to do is scale up one of the sides, and this will give us a new parallelogram with this constant times the area of the old one. However, addition doesn't quite work out as well. And remember in the last video how we sort of had an ad hoc definition for addition, where if we had two parallelograms, we could shear and scale them in order to make them have one of the vectors be the same. And then we sort of join the two parallelograms together, connecting them at that vector. And that gave us a process of taking two parallelograms, finding equivalent ones, and then finding a new parallelogram which had the sum of their areas. However, the issue in 3 dimensions is that if we only restrict ourselves to shearing and scaling, we can't ever leave the plane which the parallelogram is already in. And so what that means is that if we try and add v1 wedge w1 plus v2 wedge w2, this is going to be an issue if these lie in different planes. So for example, if we have the x, y, and z directions here, and I'll label these as unit vectors, so this is the first, second, and third unit vector, then we can look at the area spanned by the x and y unit vector, which would be x hat, wedge, y hat. And we can look at the parallelogram spanned by the x and z unit vectors, which would be x hat, wedge, z hat. And so now the issue is that these two things lie in different planes. And so you can't quite shear and scale them together in order to coherently combine them into one parallelogram that lies in a single plane. And so what that tells us is that shearing and scaling does give us a well-defined multiplication on the set, but does not give us a well-defined addition on the set. And in order to do that, we're going to have to look at the other pair of axioms that I mentioned in the last video, which I'll rewrite now. Okay, so recall in the last video, we had two different equivalent definitions for area elements. One of them was more geometric and one of them was more algebraic. And so the difference between these is what equivalence relations we're quotienting out by. And so the geometric notions pretty much got us everything that we wanted geometrically, in that for any parallelogram, it gave us a well-defined notion of orientation, and it also allowed us to compute the area of the parallelogram. However, the moment we tried adding some algebraic structure, in other words, we tried making this set into a vector space, our geometric axioms failed because we couldn't add up two different things which lay in two different planes, because if we shear and scale them, then each parallelogram will only, or the resulting parallelograms will lie in the same plane as the old one. And so we can't combine these two to make a third parallelogram which lies in just one plane. And so instead, in order to have our algebraic conditions of having a well-defined addition, we're going to move to our algebraic axioms. And to remind you of what these are, we're quotienting out by bilinearity, which encompasses these first two axioms, and the alternating property, which is this last axiom. So the bilinearity property, I should have emphasized this in the last video, but it says that if you keep one of the vectors fixed, then you can treat this as a function of the other vector. And so in other words, if you keep the first vector fixed, then we can consider this as a function of the second vector. And as a function of the second vector, it is a linear function. And so what that means is that we can either add two vectors before or after applying the function. So here we're adding them before, and then here we're applying the function first and then adding them. And scalar factors, we can either multiply them before or after. So here we're multiplying it before, and here we're multiplying it out after. And similarly here, if you keep the second variable fixed, then you can treat it as a function of the first variable. And again, as a function of the first variable, it is linear in that you can either add before or after applying the function, or you can pull out scale factors from it. And the second condition, the alternating condition, also known as anti-commutativity, says that if you flip two vectors, then you're going to get a negative sign, which says that the resulting parallelogram has the same area and orientation. Well, it doesn't have the same orientation, but has orientation which is the opposite in the sense that it is multiplied by -1. Okay, so let's see how this fixes our problem over here. And in the last video, I claimed that these two axioms and these two axioms are the same. But it turns out that in 3 dimensions, these two axioms allow us to do a bit more because of what I'm about to show right now. And the thing is that bilinearity doesn't constrict ourselves to sort of adding vectors in the same plane like shearing does. And so if we have the sum x hat wedge y hat plus x hat wedge z hat, then notice that these two share the same first component. And so we can use the bilinearity to say, okay, we consider this as a linear function of the second component. And instead of adding it after we apply x hat, we can add it before we apply x hat, and we get this expression. And this should be plus. And so what does this look like? Well, if we look at the vector y hat plus z hat, it'll be this diagonal vector. And so we can look at the plane spanned by this diagonal vector and the x hat vector, and this resulting plane will be the sum of these two planes. Okay, so this gives us a sort of a nice way to add up two planes algebraically, but it's a bit, it leaves us a bit uneasy because first off, if you add up two things in two different planes, then you're going to get something which lies in a completely different plane entirely. And so this maybe isn't too bad because if you take two vectors, if they aren't collinear, then their sum will generally lie in some line which is not in either of their directions. However, there's something which is a bit more uneasy than this, which is that each of these areas has an area of 1, so long as you dictate that x, y, and z are all orthonormal vectors. However, this resulting area coming from their sum has an area of square root 2, because x hat has an area of 1, but this vector has a length of square root 2, and so the resulting parallelogram also has an area of square root 2. So that's saying that if you add something with an area of 1 and an area of 1, instead of getting something with an area of 2, you get something with an area of square root 2. And maybe that just means that when we add up two things, we have to abandon the notion that it represents adding up the areas together, and it only adds up the areas together if the two parallelograms lie in the same plane to begin with, similar to how this will in general change the length of the two vectors, and it'll only be sort of additive for the length of the vectors if the two vectors were collinear to begin with. Okay. But a bit more pressing is whether this process can always be done. So if we take some arbitrary vectors, say 2, 1, 3, wedge 3, 5, 7, plus 3, 9, 4, wedge 2, 6, 7, can we always do this process of using bilinearity and the alternating property to get something wedge something else? And so it's not so clear that if we can do this, because the fact that I just used was that these two areas have the same first component, and so we can use the first axiom to say that, okay, we consider it as a linear function of the second one. But in general, these two guys, they neither have the first component equal nor the second component equal. So is it possible to add these together? And the answer in 3 dimensions turns out to be yes. And we're going to use a similar trick to last time, where instead of adding up these guys, we're going to find two equivalent expressions to each of these and be able to add those two together. So one thing to check is that the shearing and scaling axioms basically both fall under bilinearity, so that if you have bilinearity, you at least have shearing and scaling. So we're able to use shearing and scaling at our disposal. And what we can do is we can consider these vectors as being, say, v1 wedge w1 and v2 wedge w2. Now what will happen is, in 3 dimensions, v1 and w1 will span out some plane, and v2 and w2 will also span out some plane. And so I sort of drew out these special planes because I'm not too good at drawing, but in general, you can think of any two planes in R3. And what happens is in R3, any two planes must intersect at a unique line, so long as they aren't in the same plane. But if they're in the same plane, then it's pretty easy to add them anyways. And so in this case, the unique line that passes through both of them is going to be this line. And so we consider this line as being all multiples of some vector u. So this line is basically equal to the set of lambda u. And the point is that if we choose some vector that lies on this line, well, this line lies in both planes. So what we can do is we can express v1 wedge w1 and v2 wedge w2 in terms of something with u. So how can we do that? Well, let's restrict our attention to the v1 w1 plane. So let's say that v1 looks like this and w1 looks like this. So because the line spanned by u lies in this plane, we're going to have that u also lies in this plane. And so what this allows us to do is that we can first shear w1 in the direction of v in order to get something that is in the direction of u. So this will be like w1 prime, and the area spanned by v1 and w1 prime will have the same area as v1 and w1. And now what you can do is you can rescale w1 by some factor a to get it down to u, and you can stretch v1 by the opposite factor. And so what I'll do is this will multiply this by a factor of a and multiply this by a factor of 1 over a, and it'll leave the area the same. But the advantage is that now you have something of the form v1 prime wedge u. So the second component can be taken to be u. And similarly, you can do the same thing with v2 and w2, and you'll get an expression of either something wedge u or u wedge something. And so if you end up with the second scenario, what you can do is you can just flip them using the alternating property and throw in a negative sign. And so what that allows you to do is it allows you to find representatives for these two guys, which will look like u wedge something plus u wedge something else. And this you can write as u wedge their sum. And so what that tells you is that at least in 3 dimensions, the alternating and bilinearity property allow you to add up any two expressions and get a third one. And so in the background, there is something similar to the crossbar going on here, where, for example, in physics, you can add up two torques which are in different directions, and you'll get a new torque. And so I recommend you to try and doing this computation by taking the cross product of these vectors and then computing their sum and then seeing if you can find some pair of vectors which cross product to the same sum, and then see if that you can relate that to what I just explained. Okay, so in 3 dimensions at least, the alternating and bilinearity property get you everything that you want. In that it'll get you some description of having an area and orientation for every plane, and it'll also have a vector space structure on this set so that you can multiply anything by a scalar and you can add two area elements together. However, as soon as we enter R4, we run into even more issues, because that same trick that I just used to add up to arbitrary things, it does not work anymore. So if we let the unit vectors be E1, E2, E3, E4, and these form a basis of R4, then it turns out that the expression E1 wedge E2 plus E3 wedge E4, no matter how hard you try, this is not equal to V wedge W for two vectors V and W in R4. Okay, so now we sort of have to give up our notions a little bit of trying to add up two area elements and get a new area element. And you can try your hand at this, and I recommend that you do it. But I'll maybe explain a nice geometric way to do this later. However, our new definition will have to be modified to allow expressions like this instead of just pure expressions like this. And so what that means is that our set of area elements, we can't just have V wedge W anymore. What we'll have to have is a span of V wedge W for V and W in our vector space. So what this will mean is that this will be the set of area elements. And so these will just be formal linear combinations of things that look like this. So for example, we can have like 4 E1 wedge E3 plus 6 E1 wedge E4 plus 7 E2 wedge E4. And we also want to still have these bilinearity and alternating properties, or the shearing and scaling properties. And so we're still going to want to quotient out by these two properties. And so finally, this definition, the span of things that look like this, modulo these two things, is what is actually always written as lambda 2v, or also as v wedge v. And so this is sort of the proper final definition that we have for describing areas. And it's a bit problematic because now we're going to have to sort of abandon the notion that elements of this correspond to just areas, and they actually correspond to sums of different areas. So in other words, this expression is the sum of an area in one plane plus the sum of an area in another plane. And there's not really much that we can do about that, unfortunately. So I'll talk about something along those lines and what is going to be better to do for the Rham Cohomology in order to resolve that issue. But before I do that, I want to go on from talking about two-dimensional areas to higher dimensional volumes and whatnot. Okay, so now we have our definition of areas, which works in all dimensions Rn. And our definition is this vector space lambda 2v, which is defined as the span of symbols of the form v wedge w. And so remember, you should think about this as v wedge w representing the parallelogram that's spanned by these two vectors, quotiented by the relations of bilinearity and the alternating property. And so the way to think about this space is potentially a disjoint union of a bunch of parallelograms which have certain areas and may lie in different planes. And you can sort of shear them and scale them and shift them out of planes. And so the advantage of having this as a definition is that since we're defining it to be the R-linear span, it is manifestly a vector space in that we have defined notions of scalar multiplication and addition, which agree with our ad hoc notions developed earlier. And the bilinearity and alternating property are sort of to keep as close to areas as possible, in that it encompasses the shearing and scaling properties that we had earlier, but it also allows you to sort of shift in and out of planes since the bilinearity property is a bit more general than the shearing property. But yeah, so this is how we're going to describe areas in Rn. And so now, since we have good things to define one-dimensional objects, namely vectors, and now two-dimensional objects, why not generalize to three-dimensional objects or volumes? So for this, let's consider the case v equals R3. And this is the formal definition that we'll come to, but before that, let's trace through our steps and see how we could have come up with this. So you can start off by coming up with the same initial guess for definition, which is to take all things which look like this. And what does this represent? Well, this represents a parallel pipette that's spanned by the vectors v1, v2, and v3. And so this will represent sort of the volume that's spanned by these three. So if we draw our standard picture of R3 and take the vectors e1, e2, and e3, then we can consider the symbol e1, wedge e2, wedge e3, and look at the cube that's spanned by these guys. And we just say, okay, the symbol e1, wedge e2, wedge e3 signifies this cube. And in general, it signifies some parallel pipette spanned by the three vectors. And so again, we're running into the thing of, okay, this sort of specifies its shape, but all we care about is its volume and maybe its orientation. And so we can introduce some equivalence relations like earlier, and the equivalence relations will be pretty similar. So what we have is that if you shear any parallel pipette, you're still going to get the same volume. So for example, if you take this E3 vector and you shift it in the E2 direction or shift it in the E1 direction, or really any direction in the E1, E2 plane, then you're going to end up with the same volume. And so you can think about that as like taking some jello, right? And then you poke it in different directions and it sort of like wiggles back and forth, but never actually changes the volume. And so what that tells you is that the shearing axiom says that if you take any one vector and add to it any multiple of the other two vectors, then you're going to get the same volume. And so you can think about that for a bit and convince yourself that that's true. And then the other axiom is the scaling axiom, which holds almost verbatim, which is that if you scale any one direction by a scale factor a, then the volume also scales by that same scale factor. Okay, cool. So now this is enough to give you an equivalence relation on all volumes in R3. And I encourage you to work through this and take any three vectors, v1, wedge v2, wedge v3. And so you can either choose specific numbers, you can choose variables for each of the three components of each vector, and try and show that this is equivalent to some constant v times e1 wedge e2 wedge e3. Okay, and then what you'll find is that this volume will define it to be this v will define to be the volume of these three guys, because we want the volume spanned by the three basis vectors, if they're orthonormal, to be equal to 1. And so again, that's sort of our special volume axiom that we had earlier. And then you may also notice something about the sign of v coming into play. And so similar to how in 2 dimensions we only had orientation up to plus or minus sign, we have the same thing in 3 dimensions. And so what happens here is that if you, for example, switch E1 and E2, then you can use a similar argument from before, where you have to rotate in the E1, E2 plane, and then multiply one of them by -1, and so you get a factor of -1. Or if you switch E1, E3, then the same thing, you rotate the E1, E3 plane, and then you multiply by -1. So the effect is that if you switch any two vectors, then the orientation gets multiplied by a factor of -1. And so similar to how we did in the last video, what you can do is you can shear and scale any two parallel pipets so that two of the vectors are the same, or in essence, one of the faces is the same. And then you can sort of stick the two parallel pipets along the matching face and have a well-defined addition. Okay, so this is how we can define volumes in R3, and then we can go into R4 and say, okay, does the same thing still work? Well, similar to what we had from going in areas from R2 to R3, we'll find that yes, geometrically you have an orientation and you have a well-defined notion of volume, and here the orientation sort of represents three-dimensional subspaces of R4. And okay, you also have a scalar multiplication given by the scaling axiom, and then you could ask, does addition work? And addition works in much the same way that addition of areas work in R3, and it turns out that if you take any two three-dimensional subspaces in R3, then they must intersect in a two-dimensional subspace. And so what you can do is then you can take two three-dimensional parallel pipets in R4 and look at the three-dimensional spaces spanned by those, look at the two-dimensional plane in their intersection, and then express both of those parallel pipets as being some sort of area in that matching plane, wedge something else in their individual directions, and then sort of add up the third component. So I'll let you think about that as well. And so you also get a well-defined notion of addition in R4, but then that starts to break down in higher dimensions. And so again, you sort of have to resort to saying, okay, instead of just looking at symbols of this form, we're going to look at just the span of symbols of this form, which sort of represent disjoint unions of different volumes in potentially different three-dimensional subspaces of your vector space. So here we have our definition for what a volume looks like. This is denoted by lambda 3v, and it's the span of symbols which look like this, modulo the axioms of trilinearity and the alternating property. So again, like if you want to find addition in R4, shearing doesn't quite work, so you incorporate trilinearity, and trilinearity is sort of like a generalization of shearing, but it allows you to go out of the plane. Okay, so what does trilinearity say? Well, similar to bilinearity up here, if you fix two of the vectors, like v1 and v2, then you can consider the symbol as a function of the third vector. And as a function of the third vector, it's a linear function. So you can pull out scalars to the outside, and you can either add before or after applying the function of having v1 wedge v2 wedge this third one. And similarly, if you fix the first and third vector, it should be a linear function of the second vector. And if you fix the second and third vector, it should be a linear function of the first vector. And so that's why you have trilinearity, because it's linear in each of the three components. And then you have the alternating property. And so the alternating property says that if you swap any two vectors, then you're going to pick up a negative sign. And so remember what I said here was like if you swap E2 and E3, then you have to rotate it in the E1, E3 plane. And if you swap E2, E3, then in the E2, E3 plane, and then each of those times you multiply by -1. So for some examples, what we have is v1 wedge v2 wedge v3 equals negative v1 wedge v3 wedge v2. And so what I did was I swapped these two, or maybe you could swap v2 and v1 and get up to here, or you can go over here and you can swap v1 and v3, and then you pick up another negative sign which will cancel with this one, and then you end up with these two having the same orientation. And you can sort of try and see if you can geometrically rotate this one to get back to this one. And you can have similar things where you can alternate different combinations of these guys. And if you're familiar with the language, then what this says is that you permute the three indices, and then you multiply it by the sign of the permutation. And the fact that the sign is well-defined also tells you that you have a well-defined sign, which doesn't matter in which order you swap the things. Okay, so yeah, this is the definition of volumes. And now we can just like generalize into higher dimensional things, right? So we can talk about k-dimensional volumes. And the definition should be pretty similar. It should just look like lambda kv is equal to the span of things which look like v1, wedge, v2, wedge, dot, 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 up to vk, with all vi lying in our vector space. And our vector space is going to be some Rn. And this is quotiented out by the relations of, well, we had bilinearity and trilinearity. So in general, we're going to have something called multilinearity, which says that if you fix all the entries except one, it's going to be like a linear function in that variable. And the alternating property, which says that if you swap any two vectors, then you'll pick up a negative sign. And again, this sort of corresponds to you have to rotate in that plane, and then you have to pick up a negative sign to sort of force them back into the same orientation. Okay, so now we can define arbitrary k-dimensional volumes in arbitrary n-dimensional space, and this is written as lambda k r to the n. And this sort of a thing is called the k-fold wedge product sometimes, or the k-fold exterior product. And so sometimes I'll be using those terms in later videos. Some exercises to do is, first off, again, take any three vectors and express as this basis, and then confirm that this v that you get is the determinant of the three entries. And so that's one way that you can get to the determinant. Another important thing to realize is let's look at some of the consequences of the alternating property. Let's say that we had some repeating vector here. So let's say we had a symbol of the form v1, wedge, v1, wedge, v2. And so what this will say is you have two vectors, and you sort of look at the parallelepiped spanned by the first one repeated, and then the second one. And so what this will look like is it's just like one vector, another vector, and then a third vector like this. But you see that this is like an area. It's not really a volume. And so what you expect is that the volume should come out to be 0. And luckily it does, because what we can do is we can swap these two guys, and we'll pick up a factor of -1. And so this will say this is negative v1 wedge, v1 wedge, v2. And essentially, because this thing is equal to its negative, it must be equal to 0. And more generally, you should check that if you have any vectors which are linearly dependent, then their wedge product is going to be 0. And the wedge product is just like this sort of thing where you take wedges between the vectors. And that tells you that if your vectors lie in a smaller dimensional subspace, then they must be 0. In particular, the smallest dimension in which lambda to the k Rn is non-zero is when k is equal to n. So in other words, there's no like n-dimensional volumes in a smaller dimensional space. And the second thing that you should do is we have this sort of more abstract definition of lambda kv as sort of being the span of these guys. And so this is a vector space, and so as a vector space, we should probably determine its dimension. Exercise is to show that lambda k r to the n, let's say that r to the n is the span of some vectors e1 all the way up to en. Then lambda k, you can span them by the vectors or by the volume elements. Let's say I1 wedge I2 all the way up to EIK, such that I1 is less than I2 is less than all the way up to IK. So what this is saying is that you can take any k-dimensional volume, and split it up into formal sums of volumes lying in sort of the coordinate plane. So in R3, it'll say that the span of lambda 2 R3 is E1 wedge E2 plus E2 wedge E3 and E1 wedge E3. So you can take any plane in R2 and sort of decompose it using the bilinearity property to get something which lies in this plane, get something which lies in this plane, and something which lies in this plane. And the increasing property pretty much says that the indices here should be increasing. So I have 1, 2, 2, 3, and 1, 3, as opposed to say 3, 1. And so the reason for that is to remove the redundancy that's given to you by the alternating property. And based on this, you should verify that the dimension as an R vector space of lambda k r to the n is equal to n choose k. Okay, nice. So now we have finally finished a description of how to describe volumes in R to the n. Or at least we've almost done so, because we have this still little annoying feature that these aren't just like k-dimensional volumes in n-dimensional space. There are formal linear combinations of them. And sure, when you have vectors, you have components in different directions, but it's still represented by a single arrow. But here, we can't represent it by a single k-dimensional volume. We have to represent it by sums of k-dimensional volumes in order to have any sort of vector space structure at all, which is a bit annoying. So how we're going to resolve that is finally go back to the special area axiom, which I've been neglecting for a while. And what we'll find is that we actually have to sort of reorganize a little bit of what we'll do here, but we'll finally have the proper notion of how to describe volumes, which will be suitable for introducing calculus and talking about Rham cohomology.